All right, so as I was saying, I didn't assign you a textbook because we're not going to be doing any work out of the textbook this semester. But the textbook is shared with you in that folder along with the solutions manual. So the textbook sections are references to you that if you go through a lesson and at the end of the lesson you feel as though that didn't do it for you, then you can always pull up the file for that particular section in the textbook and you can go through those examples if you like. So it covers chapters 1 and 2. We're basically dealing with what's called transformations in this first unit, and we're dealing with 3 specific transformations. This is the beast, and this is something that you need to have a very good handle on in terms of your understanding, because we're going to be applying this in Unit 2 to polynomial functions, and in Unit 3 to trigonometric functions, and in Unit 5 to exponential and logarithmic functions. And it spiderwebs out. It's very important. You don't know what that means, and that's fine. If you knew what that meant, then I could go home, right? We're also going to be looking at this transformation. A transformation is a change in something. So y equals f of x, whatever that is, it's a function, changes to g of x, which is a times f of b times x minus h plus k, whatever that means. We can also take y equals f of x and change it to x equals f of y. That's a type of transformation we're going to learn about. And the third type of transformation is we can take y equals f of x and transform it into a new function, y equals the square root of f of x. So this is on page 1 of your unit handout. We're looking today at horizontal and vertical translations, and we will continue to do a little bit more with this topic tomorrow. So again, that's a textbook section. What's in the box is always just an objective. I put them in there maybe more for my own sake. I don't think it's that important for you. You look at that and you go, okay, that's what we're doing today. Maybe at the end of the lesson, you can look at it and go, oh, okay, I know what that means now. And at the end of the lesson, if you look at it and go, I don't know what that means, then something didn't work out. So this is the goal today. And again, you're not going to really understand this for a little while in this lesson. We're going to take a function, which is a graph or an equation or a relationship between variables. The function will be y equals f of x, and we're going to transform it into a new function, which we're going to call g of x, and there's a connection between g of x and f of x. It turns out that g of x is described as being f of x minus h plus k. And our goal is what happens. So when you change the equation of a function, functions can be graphed. If I say to you, what does y equals x squared look like, you know what it looks like, I hope. It's a parabola with its vertex at the origin, opening up. So that's an equation, y equals x squared. If I change that equation, the corresponding graph will change. So when a function undergoes a transformation, a new function is produced. The word transformation means to change. One type of transformation is called a translation. So a transformation is a broad category of things. We can have reflections, that's a transformation. We can have stretches, or we can have translations. And translations are what we're dealing with today. A translation occurs whenever a graph of an original function is translated to a new position. That's it. Yeah, I think in somewhere in junior high, you might have done this with shapes and called them slips or slides, or I don't know. Might even be an elementary school thing. During the translation, though, the shape of the graph, the orientation of the graph, the size of the graph doesn't change. It doesn't get taller or narrower or wider or shorter. It doesn't turn upside down or rotate in any way. It stays in the same fixed orientation and size. So I want to take you back to Math 20-1. You should be familiar with y equals x squared. You should know what this looks like. And this is not in your notes. I'm just asking you to follow along here. And in Math 20-1, you learned that there's a connection between y equals x squared and this function, which is y equals x minus 3 quantity squared plus 4. What you learned is that, and I hope you remember this, the vertex of the original, I'm going to call the yellow graph the original, the vertex is at the origin, but there's a connection here. How many of you recognize what just came up here? X minus p quantity squared plus q. We learned in Math 20 that when you have a quadratic function, like the one highlighted in blue, that's in what's called the vertex form, the vertex has a location of p comma q. So since it's x minus 3 quantity squared and this is x minus p quantity squared, that means the x coordinate of the vertex is 3 and the y coordinate is 4. Ring a bell? Okay, so what we want to do this year is we want to say to ourselves we have an original and we have a transformation of the original. We have a new function, original and new, but we want to make things more general and say what's happened is the original function has been translated 3 units to the right and 4 units up. And for reasons that should become clear over the coming days, well, I'll get to something else in a bit. So what we would say is that's the translation that occurs, okay? And I hope that rings a bell. If that rings a bell, you're already kind of understanding what's going to happen today. So what we sometimes do is instead of, if you look here, the original function is y equals, and the new function is y equals. It's nice to be able to distinguish between the two by slapping labels on them, names on them. And what we typically do is we call the original function f of x and the new function g of x. We don't have to. You can call the original function p of x and the new function r of x. You can use whatever letters you like. But this is kind of standard practice as we warm up here. So rather than saying y equals x squared and y equals x minus 3 quantity squared plus 4, we can say f of x equals x squared. And g of x equals x minus 3 quantity squared plus 4. Okay? So that's the original, that's the transformation. Let's take a look at example 1. And just a reminder, if you do have a question, you need to raise your hand. An original function is transformed to produce the new function shown. The original, you're told, is f of x. The transformed, or the new function, is g of x. I don't like to use transformed function. I don't like that phrase because transformed can be a verb or an adjective. And if I use the word transformed as a verb, I'm talking about transforming f of x. I'm saying f of x is going to be the transformed thing, the thing that's transformed. But if I talk about the word transformed as an adjective, then g of x is the transformed function. English is tricky, trickier than math, I think. Okay? So I like original and new. State the horizontal and vertical translations that f of x undergoes to become g of x. So I want everybody to take 10 seconds and figure out how far to the left or right, that's what the word horizontal means, to the left or right. How far to the left or the right f of x moves, and how far up or down, up and down means vertical, it moves to become g of x. I think this is pretty straightforward. It's translated 4 units to the right and 9 units down. And I hope that isn't a brain buster this morning for you. Okay. What we are saying, and I'm not going to go through every single point. I had to add something here. What we are saying is that if you take, for example, the point A, it becomes this point, which is called A prime, that kind of hash mark, that line above the A is A prime, and that's accomplished by moving A 1, 2, 3, 4 to the right, and 1, 2, 3, 4, 5, 6, 7, 8, 9 down. We're all okay with that, right? And if every point on the original function follows the same transformation, then you're going to have the same shape. It's not all smeared or twisted. Okay. So I've given you the domain and range of the original function, and what I'm going to do is just freeze the graphs up here so we can refer to them. I've given you the domain and range of the original function. The domain is everything from -5 to 3. So when we say -5 is less than or equal to x, and x is less than or equal to 3, we are saying that -5 is the minimum value that x has anywhere on the whole graph. There's no point on the graph with an x-coordinate less than -5. And the maximum value of x is 3. So if you were to, look at the blue graph up here on the screen that's frozen and sweep this arm or line left to right, the first point occurs at x equals 5. Then x increases, 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 and the highest point or value of x is 3. Okay? We want to use this standard practice of putting the minimum less than or equal to the variable less than or equal to the maximum. However, there is a way to write it in a different fashion, and it's to say square bracket -5 comma 3 square bracket. This is not an ordered pair. It's not an x comma y. It's a way of saying -5 to 3, including -5 and 3. And not that it really matters for this example, but the reason why we have square brackets is because x can equal those numbers. If it turned out that this was the graph, which is kind of a weird situation, that the graph kind of starts over there at x equals -5, but there's no point at -5. Then, if that were the case, then this would be the domain. And that's something you learn about in Math 10 and Math 20. Okay? However, that is not, in fact, what it is. So, and then we can take a look at the graphs on the screen that's frozen. The blue graph has a range from 2 to 4. Are we okay with the domain and range? Okay, so I want you to just take a minute and write down what the domain of the red graph is, what the domain of the new graph is. So you're going minimum. It's continuous everywhere, so it will be minimum less than or equal to x, less than or equal to maximum. And I'm getting -1 is less than or equal to x, which is less than or equal to 7. And if you haven't had me as a teacher before, I'll just remind you, you should be thinking and doing this on your own. You shouldn't just be waiting for me to write something down so you can write it down. Okay? Of course, I can write that as this. I like to put that x with a colon in front of that other notation, because if you don't know what you're talking about. You're talking about x, you're talking about y. I think it's important. And take a minute and identify what the range of that function is. And I'm looking at the red graph, and I can see that the minimum value of y is -7, and the maximum value of y is -5. So does anybody have any questions with finding the domain and range of the new function? Here's food for thought, though. We did not need to look at the graph to determine that, because you've already established that f of x is transformed 4 units to the right. Think about that. F of x goes 4 units to the right. Wasn't that what we said? So every x coordinate ought to increase by 4. And if I take the minimum value of x on the original function of -5 and I add 4 to it, I get -1. If I take the maximum of 3 and add 4 to it, I get 7. We also know that the original function was transformed 9 units down, right? That's what we said? So if I take the minimum value of y, the graph had a minimum value of y up here at 2, and it moves 9 down, I don't care about moving left, right in my head. If it moves 9 down, I take 9 away from 2, and that gives me negative 7. And at this stage, I hope you wouldn't have to take your calculator and go 2 minus 9. You have to be comfortable working with these numbers. They're just integers. And if I take 9 away from the maximum value of y, I get negative 5. So that's an important idea. Mapping. This whole first example is about kind of an introduction to some of the terminology. Mapping describes what happens to a specific point during a change in the function. So when I take a look at the coordinates of point A is at negative 5 comma 2. A prime, its sister point, its twin, I guess, I don't know what you want to call it. If you read it, it's at negative 1 comma 7. Or negative 1 comma negative 7. You don't really need to look at the graph. Because again, if you shift something 4 to the right, every x coordinate is going to increase by 4. So negative 5 plus 4 would give you negative 1. Because negative 5 is an x coordinate. And you're shifting everything 9 down. And this 2 here, this 2 is a y coordinate. So it's going to be affected by the vertical translation. And if I shift something that's at a height of 2 down 9, it's going to be at negative 7. So to complete the mapping here for just a couple of points I picked, we can either look at the grid. So for example, when I look at C prime, it's at 3 comma negative 5. Or what we could do is use kind of this rule that says x is going to increase by 4 and y is going to decrease by 9. I'm going to use the rule for E. If x is at 3 and it increases by 4, the new x will be 7. And we want to take 9 away from the y coordinate, which also happens to be 3. That gives me 7 comma negative 6. And then we come up with the most important thing. What this means is we have this mapping rule for this example. That x comma y becomes x plus 4 comma y minus 9. All right. So I'm going to show you now the notation that we use. I'll show you the notation. It's not going to make a lot of sense, but with example 2, it will all start to come together. Okay? When an original function is changed from y equals f of x to y minus k equals f of x minus h, I just want you to notice something, and it's not really important, but some of you might find value in seeing this. That what happens here is you're changing x to x minus a number, and you're changing y to y minus a number. That's what's happening. You're taking the equation of the function, and if there's a y, you're changing it to y minus k. And every place there's an x, you're changing it to x minus h. So when you do that, when you make these replacements, it turns out that the new graph will be shifted left, right, up, down, depending on the nature of h and k. So I want us to refer to y equals f of x as the new function, and then this is the original function. The new function is y minus k equals f of x minus h. The only issue is nobody walks around saying the equation of the function is y minus 3 equals, or y plus 8 equals. We like y equals. So you may see things written that way, but this is better. Okay, much better, more familiar to us. And as I mentioned before, it's nice to do that. It's nice to say g of x equals. That way we distinguish between f of x being a function and g of x being a different function. Okay? This is preferable. So this is what we're talking about today. So h, whatever h is, it's a number. We call it a parameter. Don't worry about that word just yet. We're going to keep coming back to it. I try to use it in my Math 20 classes with you. And h is the number that tells us about the horizontal change, the horizontal shift. K is another parameter, and it's a number that tells us about the vertical change. And f of x can be any function. So if you know h and you know k, you can tell me what's happened without using a graphing calculator or anything else. So now we're going to work through an example together. And the example is going to go through a number of scenarios with different functions and different h and k's. But keep in mind, we are always comparing the original function, everybody, to this. This is our template. We're always comparing what the new function is to this thing, because this is the new function. So I want to go back because I used different language there. The new function is this thing. When I say this is the new function, you're going to take whatever I just showed you and compare it to what I've highlighted. So, for all of these, we're given a transformation. We're given an original function and a transformation. We are asked to write the value of h and the value of k. We're asked to determine the equation of the new function. And then we're asked to explain or describe what's happened to the original to get the new. So the first one says we're going from f of x equals x squared to y minus 3 equals f of x minus 4. You with me on that? Okay. That's okay. You're likely to see this more often. And that's the most informative. By the way, I should point out to you, I didn't, but you will notice that when you look at this form that's highlighted in yellow, it's y minus k equals, but in the other forms it's plus k because k has been added to the other side. Right? I hope you understood how I went from the yellow to the next one. All right. So, how do we determine h and k? We compare this template that's up on the screen in red to the function given in the question. And I hope it's clear that we can see, since it's f of x minus 4, and we're comparing it to f of x minus h is 4. Okay, so we know h. And since it's f of x minus h plus k, and our function is f of x minus 4 plus 3, k is 3, right? Okay, so now let's write out the equation of the new function. Well, how do we do that? Okay, let's take a little break here. If I say f of x is x squared, and I said to you, what is f of 3? Then that means put 3 in for x, right? Which gives us 9. You learn about this use of function notation in grade 10. If I said to you, what is f of negative 4? Well, then you would put negative 4 in for x, and you would get 16. The point is, if I said, what is f of puppy? It would be puppy squared in this case. So if I say, what is f of x minus h? It's x minus h squared. So when I have, I'll just write this here. I know it's already written down for you. F of x equals x squared. And I want to find the equation of this function. F of x minus 4 plus 3. This part is simply going to be x minus 4 quantity squared. The f of means we're going to replace x in the original function with x minus h. In this case, x minus 3. So this is the equation of the new function. Any questions with that? So you could do this on your graphing calculator, but I have the graphs for all of our examples today loaded up here. There is f of x equals x squared. You can see it's labeled in the top right corner of the screen. I'm going to graph now f of x is equal to x minus 4 quantity squared plus 3. no surprise, it's shifted 4 to the right and 3 up. You know this from Math 20. You shouldn't even need to talk about x minus h or anything. You'll notice, by the way, I'll just throw this out and hopefully it sticks, that we're not talking about p and q, we're talking about h and k. But those are just letters. They're just squiggles on paper that we decide what letters to use, and we use h and k. In a later on unit, we'll use c and d. It doesn't matter. So the answer to this question, it's 4 units to the right and 3 units up, correct? Okay, so you'll notice that h is 4 and that k is 3. Eric, what is there, do you think, about h that's telling us it's to the right?
What do you mean?
Well, why is there a case you think where it might be 4 to the left?
If it was negative 4, it'd be to the left.
Right. So we're trying to tie the sign, we're going to be tying the sign of the parameter to the direction of the translation. K happens to be a positive number, and up is positive. So what is the mapping? The mapping is that. X plus h, y plus k. Let's try another one. So this, I'm going to pick up the pace a little bit here because the only thing that's different in the B, C, and D is the original function is different. So now I'm not talking about f of x equals x squared. I'm talking about f of x equals the absolute value of x. But again, when we compare, everybody, g of x equals f of x plus 2 plus 4, which is the question, to the template in red, you ask yourself, what number do you put in for k to make that happen? And the number you put in for k is 4. Correct? You're with me on that? Okay. So k is 4. The question now becomes, what number do you put in for h in x minus h to end up with x plus 2? Eric, do you know? I'm asking you, what number do we put right here so that this is going to turn into x plus 2? Negative 2. And you might remember from Math 20 that when you were looking at the x minus p quantity squared, p was actually the opposite of the number that you saw in the equation. But k was just, or q was just the number that was there. That's where this is coming from. So if we had to make a prediction, whatever this original function looks like, our prediction, based on what I've told you, is that this function should be shifted 2 units left and 4 units up. And if that's the case, then the mapping should be that x comma y maps to x minus 2 comma y plus 4, which it will. It will. But the only way to convince you of that is to graph both functions, and the only way you can graph the new function is to determine the equation of the new function. So we have g of x equals f of x plus 2 plus 4. So what does f of x plus 2 mean? Well, if f of x, and I'll write this down just so we can focus our attention on it, if f of x is the absolute value of x, then f of 5 is the absolute value of 5. F of pi is the absolute value of pi. F of 37 over r is the absolute value of 37 over r. F of x plus 2 is the absolute value of x plus 2. So this is the equation of the new function. So let's see if our prediction is right. I hope you're familiar with the absolute value of x as a function from Math 20. I'm not saying you should have known that's what it looks like, but when I show it to you, you go, oh yeah, I remember that. Okay? And I don't want to get into a discussion of absolute value here. That's not what's important. This is what it looks like. And when I graph the absolute value of x plus 2 plus 4, we can see that every point on the blue function has been shifted 2 to the left and 4 up. Any questions with B? Right? So in C, we have f of x equals root x, and it's transformed into, you have all these different ways of writing it, but once again, I prefer this final form where we use g of x, or h of x, which is weird. Sometimes you'll see h of x equals. That h is not h, the parameter h. Sometimes we use the same letter for multiple meanings. I would like everybody to write down in this example what the value of h is, what the value of k is, make a prediction about the horizontal and vertical translations, and the mapping. I want you to do everything except for the equation of the function. Am I going too fast? Going too fast? Going too slow? Goldilocks, eh? Just right. All right. So I'm getting h equals positive 3 and k equals negative 5. And by the way, this is the way I always explain this to people. This is pretty basic, I think. But you're going to stumble. You're going to be going along, and all of a sudden, you'll write down the wrong thing. It's very easy to make a mistake. It's x minus 3, and we're comparing x minus 3 to x minus h, so h is 3. And it's plus k, but we have negative 5 there, so we have to add negative 5, which means k is negative 5. So we're all in agreement on that. Okay. What does that mean? It means that based on what we've learned so far, we would make a prediction, and it will be a correct one, that the original function will be translated 3 units to the right, because h is the horizontal parameter, and it happens to be positive 3. And it will be translated 5 units down, which would mean the mapping would be x plus 3, comma, y minus 5. We're all in agreement on that. Okay, so what's the equation of the function? Well, the function g of x is equal to f of x minus 3 minus 5. What is f of x minus 3? Well, f of x is root x. F of mouse is root mouse. F of desk is root desk. F of 5 is root 5. F of x minus 3 is root x minus 3. I like to put that little overhang on my roots to just tell me that's where it ends. And then this minus 5. Your k, by the way, is kind of an afterthought. It's something that's added on after you apply the function. So let's just confirm that this is right now. It turns out that this is what y equals root x looks like. We want to graph root x minus 3 minus 5. Let's see, it shifted 3 to the right and 5 down. Okay, so just burning through D now. If I go from y equals f of x, which is sine of x, to g of x equals f of x plus 30 and then minus 4, I think it's pretty clear that h is negative 30 degrees. I'm going to put the degree symbol there because in mathematics at this level, if you don't put a degree symbol, you mean a different unit called a radian, which we will learn about, but this is in degrees. And k is negative 4, right? If f of x is sine of x, I'll write it down again, although sooner or later you won't need to keep seeing this approach. Then g of x is f of x plus 30, which would be sine of x plus 30 degrees minus 4. The horizontal translation will be 30 degrees left. The vertical translation should be 4 units down. And the mapping will be x minus 30 comma just trying to decide if I need an extra set of brackets there. I'm just going to put the degree symbol here, comma y minus 4. Are we okay with that? Okay, you could certainly graph this on your own, but I've got things set up for you here. That's what y equals sine of x looks like. It's what's called a periodic or a sinusoidal function. And here is what x plus 30 minus 4 looks like. I mean, we can take a specific point. You could take that point right here that I've highlighted in blue, and it turns out that that's where it is. It's 30 degrees to the left, and it's 4 units down. And you could follow all of the points that way. Now, before we go on, I think you get the gist, but I want to point out to you that if h is negative 2, the mapping is x minus 2. If k is 4, the mapping is y plus 4. It's always x plus h, and if h is negative, you'll see a negative there, and y plus k. So here's what we have learned, I hope. When you make this change, so this is the top of the next page. When you make this change, h is the parameter that tells you about the horizontal change to the function, and it's to the left if h is negative, because negative means left, and it's to the right if h is positive. The amount of the horizontal translation is the absolute value of h. All I'm saying, everybody, I want to be very clear here, is that if h is negative 8, we would never say the translation is negative 8 units. It's 8 units. Then we would say left. The vertical translation is down if k is negative and up if k is positive. Again, k is the vertical parameter, so a positive parameter means a positive change. And for vertical, positiveness is towards the sky. And the amount of the translation is, again, whatever the parameter has for an absolute value. This is just reminding you what absolute value means. I don't know that it's really necessary, but I decided to put it off on the side there. So the rules are going to work whether you know the equation or not. And this is what I alluded to yesterday, is it's not always going to be the case that you can put it into your graphing calculator and look at the new function. It's not always possible. So let's take a look at a few more examples, and then we'll be done. And again, I just want to double check. Am I moving too fast? Okay. So example 3. Write the equation of the transform function in terms of the original function. So people would look at this. If we hadn't done anything and I said, we need to write the equation of this, your mind goes in a different direction. It goes, well, it's not quadratic, so it's not an x squared. How am I going to come up with an equation? You can't. But you can come up with an equation in terms of f of x. We need to first of all identify the values of the parameters h and k. So take a minute, look at the original function, which is f of x, and look at the result, which I'm calling the transform function, which is g of x, and write in what h and k are equal to based on what you're seeing. I believe I'm seeing 4 to the left and 9 down. Okay. So what does this mean? Well, g of x is going to be f of x minus h plus k. All we do is we put those parameters in, those values of the parameters in where they belong. So if h is -4, then g of x will be f of x minus -4, and then it's plus k, which is plus -9. Now, this will probably be the only time I'll ever write that. What I would do in instruction is I would say f of f, and watch what's happening on the screen, f of x minus -4. That's what I would do. Plus k, I would just say minus 9. So we want to write this. We don't want to write, x minus negative. We just want to write x plus. Still good? Okay. This one. Now, you could, if you want to, not even worry about h and k. You should be able to look at this and go, I need to shift 10, 20, 30, 40, 50, 60. Nope. Each of those are 5. 5, 10, 15, 20, 25, 30 units to the right. Correct? Okay. Well, if that's the case, then I know it's going to be f of x minus 30. Because I recognize that when you have x minus 30, it's shifted to the right 30. So I've never, in this example so far, I've never come out and said h is 30. I'm just saying I know that x minus 30 is to the right 30. And I'm shifting up. Well, I'm going from 15 to 25. I'm shifting up 10. So I should be able to just say plus 10. Right? These blanks are here maybe to help you and to formalize what we're doing, in that we're putting those parameters in here and getting the result. Each of the following transform functions are given. What are the values of h and k? And describe how the transformations that occur. Can you do me a favor, because I changed my notes and for some reason my brain is clicking on this. Do these match your examples? Okay. So, I hope you ought to be able to look at A here and tell me that whatever f of x looks like, h of x is shifted 5 to the left and 7 up. And you ought to be able to look at B. Well, we'll get to B in a second. So the bottom line here is h is -5. I did say 5 units left, didn't I? Okay. And k is positive 7. It's really at the heart of it, at the base of this entire lesson. This is it. It's not complicated. It's going to get more complicated as the days go on, but right now it's a pretty basic idea, which is why tomorrow we're going to have a quiz on it. Probably 4 or 5 multiple choice questions or numerical response. The issue with this is, so let me ask you a question. I hope that everybody is in agreement that you look at this and you say h is 2. By a show of hands, how many of you know that k is -10? Now, those people that have their hands up, do you know that because in your brain you've already moved this over here to the other side? And I think that's what most people would do. I think most people would rearrange this. It's not much of a task to rearrange this so that you can compare it to our template, right? Bottom line is 2 units right and 10 units down. And again, as I said, you're going to stumble. I think I stumbled earlier, didn't I? Didn't I say left when I meant right? Or it's going to happen. Any questions with example 4? Number 5, a transform function has the equation of y equals f of x minus 4 minus 6. And the point 2 comma negative 7 is on that function. I don't know what the function looks like. It could be quadratic, it could be cubic, it could be exponential, logarithmic, whatever. But that point is on there. What are the coordinates of the transformed point? So in this context, transformed point means the resulting point. So f of x, the original function, contains the point 2 comma negative 7. The new function, so this is f of x minus 4 minus 6, and this is simply f of x. Right? There's no g of x here, so you got to kind of really be careful about what's the original and what's the new. What are the coordinates of this point going to be? Well, there are a couple of ways that you could do it, and I think one way is just an informal way. It's to look up here, everybody, forget about h and k, to look at this and say, well, I need to shift the original function 4 units to the right. And that means that the x coordinate goes from being 2 to 6. Because to the right means increase x by whatever that number is. And I could look up here and say this negative 6 means I'm going to shift things down 6 units. So I could take the number negative 7 and take 6 away from it and get negative 13. And would you be in agreement on those numbers? Okay. See, a more formal approach, though, and there's nothing wrong with the more formal approach because it might be needed at times, is to say that the mapping is always this. This is what we've learned. This is what we've learned today. And when you look up here, h is 4 and k is negative 6. So the mapping is that x comma y maps to x plus h. Well, h is 4, so I'm just going to write plus 4, comma y plus k, which is negative 6, so I can write minus 6. So what this means is you're simply, you're doing some algebra here. It's very limited, but whatever x is, the old x goes here. Right? So if x was 2, we're going to put a 2 here. And this, I know, for many of you is overkill, but there will come a time where mapping like this will be needed to wrap your head around what's happening. It won't always be as simple as, 4 to the right. And similarly, we're simply going to take the old y and put it here. The new y will be y minus 6. Any questions with example? Is that example 5? Okay. One more example. Sorry, I was just trying to figure out what was going on there. There's a graph of f of x. What are the domain and range of the graph of f of x minus 9 plus 37? Well, I'm going to write out what the domain of the original function is, and I'm going to use this notation. I don't have to. I can use the other notation with the less than or equal to's and the less than or equal to's. But I can see that the minimum value of x on this graph is negative 2 and the maximum value is 1. So I can write this for the domain and for the range. The minimum value is negative 3. The maximum value is positive 3. Let's see, negative 2 to 1 for x, good. Negative 3 to 3 for y, good. Those are the original domain and range. you have to step outside of the concrete in this class. You can't say, okay, I'm going to extend this grid, and I hope that nobody would do this, and I'm going to take this line and shift it 9 to the right and 37 up, and then look at the result, right? You need to, in some way, employ a mapping in that x comma y on the original function will become x plus 9 comma y plus 37 on the new function, because it shifted 9 to the right and 37 up. Now be careful here, I'm talking about mapping, which is x comma y, but when we take a look at negative 2 comma 1, these numbers are both x's. So for that part of the mapping, we're going to apply it to all of the x's. We're going to apply it to the minimum of negative 2 and the maximum of positive 1. So we're going to add 9 to both of them. So the new function, which I'm going to use g of x even though we don't have it in the question, will have a domain of 7 comma 10. So the minimum x was negative 2, but everything shifted 9 to the right, so I add 9 to negative 2 and get 7. The maximum x was 1. If I take this point here and I shift it 9 to the right, it's going to be over at 10. It's also going to have a vertical change, but it's going to be at 10. And my y? Well, for my y, what I need to do is use a different rule. I need to use this rule. So I take negative 3 and I add 37, and I take positive 3 and I add 37. How's my addition? Good? Okay. That's it. We're done. I hope that made sense to you. Really, the bottom line is you're talking about going from y equals f of x to y equals f of x minus h plus k. If you choose to call this y equals, in the blue highlight, g of x or p of x or r of x, feel free. Tomorrow we will be having a quiz on this. There are 8 questions that are multiple choice numerical response that I want you to work on. And you have lots of time. You have 15-ish minutes. A point to be made, though. When you write a Math 30-1 exam for multiple choice and numerical response, if you read a question and you look at it and you go, oh, this is easy, maybe it is. But think again, because it might not be. And every time I assign this group of questions, there are a number of people that get to a certain question and their hand goes up and they say, you've got the answer wrong in the back. I do not have the answer wrong in the back. You just need to read the questions carefully because sometimes there's a wrinkle. In this problem set, I think there's one wrinkle. All right, so get to work. I'm going to make my way around the room in just a couple of minutes to see how it went today with you.